Hi, I'm Dr. A.J. Kumar, PhD. We're once again reading the Glow-in-the-Dark Guide to Algebra, also known as Artin's book, Algebra. There will be a link to it to buy it in the description. Alright, so we're reading section 1.5. This is about permutations. So this is sort of our, first introduction to group theory. A permutation of a set S is a bijective map from a set S to itself. So I should explain what bijective means for those who aren't familiar with the CIA's function terminology. So every function has the property that a function in math is like a function in a pure functional programming language, in the sense that let me give you an example of something that is not a function. Rand. In a programming language, if you get a random number, the function has to be deterministic in the sense that you call it with the same arguments and you get the same outcome every time. So functions have to be deterministic. And there's no such thing as real randomness in computing, but you know what I mean, is that getting a random number does not return the same value. Referentially transparent, that's a better term. And we're going with green because we're reading the Glow-in-the-Dark Guide to Algebra. So referentially transparent means that if I call it with the same two arguments, or if I call it with the same arguments, I get the same outcome. So in particular, this means it is not, emphasize not, a one-to-many map. Okay, and then, so bijective means it is both injective and surjective. So injective means it's a one-to-one map. Means that it's not a many-to-one map. So in particular, I'll give examples of all of these. And surjective means every point in the target space is in the image of a function. So let me give you some examples of functions that are one but not the other. Alright, so okay. So a function, let me give you so I'm going to draw some axes here. Okay. So if I do the two-branched square root function, so this is the curve x is equal to y squared. This has two branches. This is, if we're thinking of this value, this axis as being x, and this value, the y value, as being the function applied to x, this is not a function, because it's not single valued. It's a one-to-many map. So this is not a function, not even a function. All right, and then, okay, let's go with let's go with a symmetric function, and I'm going to try to draw another parabola. Wow, that's a bad parabola. This is y is equal to x squared, and we view it as a function. This is y equals f of x, and this is x. So if now we get into mathematical fancy mode. So this is a this is a function, is not injective. And if we view it as f from the rationals to the rationals, it's not injective and it's not surjective either. Because, for instance, if I take y is equal to minus 1, there's no rational number such that when you square it you get minus 1. And it's not injective because it's symmetric. So in particular, it's a many to one mapping. So if I take minus 1, x is equal to 1 and x is equal to minus 1, they map to the same value, and that's true for any pair of x and minus x will always map to the same value. So this is not injective and not surjective. Let me think of another example. So can I think of something that is injective but not surjective? Okay, if we only take the positive branch of the square root function. So, let me make that bigger. Sorry, I forget about the new monitor. This is y is equal to the square root of x, never mind what the square root means. How you actually calculate a square root, that's not important. You could say x is equal to y squared and y restricted to, it doesn't matter. This is so this is a function f from the non-negative rationals to the ration. If we view it as to the rationals, this is a function. It is injective because it's a one-to-one map, but it's not surjective because I can't invert any of the y values down here. Okay, so for determining if something is a function, you use the so if it's a function, you use the vertical line test. So to test that, what I mean by that is can I draw a vertical line that intersects the curve in 2 points, and if I can, then it's not a function. So here, let me switch to a different color. Here, no matter which vertical line I draw, it will intersect the curve in at most 1 point. Okay? Here, again, if I draw let me switch to a different color. Here, if I draw vertical lines, it'll intersect the curve in at most 1 point. For injective, you do a horizontal line test, and this applies in general, not that's anyway. For injective, you do a horizontal line test to see. Well, it's sort of the opposite of the idea of a function, which is it. So function, this will detect if it fails the vertical line test, fails, then it's a one-to-many map. And then so for the injective horizontal line test, and then if it fails, let me save this because this is if it fails, this is a many-to-one map. If it fails, it's a many-to-one map, and then surjective. For surjective, what it means this means you sort of do another horizontal line test, which is every horizontal line intersects the curve. In at least one point. So for this is a function that's injective but not surjective. Let me draw a function that is surjective but not injective. Okay. So this would be like a cubic curve. So the point is, I draw a horizontal line down here. So no matter which horizontal line I draw, it will intersect the curve in exactly one point, or in one or more points. If I draw a horizontal line here, it intersects the curve in 3 points. The vertical line test always passes, so it's definitely a function. And so a bijective curve has the property that it is both injective and surjective. So for bijective, let me switch to another color. Bijective. Every horizontal line intersects the curve in exactly one point. In other words, if we were to so what this means is that if we reflect along the y-x-axis, then a bijective function, so in other words, if you reflect along, if you flip the axes, then curve passes vertical line test. So by this I mean reflect. So if you flip the axes and you reflect along the vertical line test, then the curve passes, or let me draw an example. The logarithm, that's an example. Okay, the logarithm is an example as long as you restrict the domain. I don't like the natural log. I'll use the natural log. We're doing glowy math, so the natural log, as long as you view it from 0, infinity, to, well, you're not going to get very many rational numbers, so we're going to use the fake real number system that the CIA invented to make sure I'm recording with the right microphone. I am. If you use the CIA's real number system, then the natural log is an invertible function, and so by that what I mean is you take the line, I'm going to try to draw it as best I can. This is the line y equals x, and then you reflect over this line, you get instead the most important function in CIA mathematics, which looks like this, and this is y, if we, so if what, let me write this as, if y is equal to the natural log of x, then, and so here's the graph I'm going to do. Okay, I'm going to draw this in the same color, and that way it's less confusing. And so, well, all I've done here is flip the axes, so this is still the x-axis, this is the x-axis, this is the y-axis Here, this is the x-axis. Here, this is the y-axis. If I flip the function along the axis y is equal to x, now I have, over here I had y is equal to the natural log of x. Well, if I invert that, I now have x is equal to the exponential function of y, which is a CIA psyop, or e to the y if you prefer. But I prefer to think of it as the exponential function. Because the exponential function makes sense. E as a concept makes less sense to me. So the exponential function, you can write it as a power series, so you can at least get some idea about how to compute it. This is the most important function in CIA math. CIA really wants you to learn about the exponential function. What was I going to say? Okay, so my point is now this is a function xp from the reals to 0, infinity. Okay. Oh, I hope you've seen this notation before. This is standard notation. So a square bracket means it includes that. This is an interval, so all numbers between 0 and infinity. A square parenthesis means it includes the endpoint, and a round parenthesis means it doesn't include the endpoint. That's what that means. So inclusive, and this is exclusive. That's what that notation means. Standard math notation, sorry. So anyway, the point is that if you can now solve, so if this passes, in other words, if it's bijective, it passes every horizontal line test. Well, that implies that when we flip it, it will pass every vertical line test, right? In other words, we can invert the function. So a function is bijective generally, not just a function from rationals to rationals or a curve or anything like that. I'm talking about a general function from one space to another space is bijective precisely when it is invertible. Okay? So if you have f from A to B, the CIA's definition of invertible is there's another function g from B to A such that g composed with f, well, this is a function from A to A, and g of f is the identity function on A, and then f of g, this is from B to B, g of f is the identity function on B. If both of these properties are true, the function is invertible. That happens precisely when the function is bijective. This is called left invertibility, meaning this is a left inverse. And I'm going to get this wrong, but I think left invertibility must mean that the function is one-to-one. And then I want to give you some hint about some Joggerlicious terminology in a minute, because there's a mapping being one-to-one. Sorry. Glowy terminology. A 1-to-1 mapping, this means bijective. The property of being 1-to-1, a mapping being 1-to-1, this is injective. So there's some wonderful glowy terminology for you. Left invertibility, that must mean that if f was a one-to-many mapping, we wouldn't be able to. Then G must be a many-to-one mapping, and that's not a function. So left invertibility means one-to-one. So this is often given as the definition of injective is there exists a left inverse. They're equivalent conditions. And then right invertibility, that must mean for every... So functions in math, you're not allowed to do partially defined functions. A function has to be defined at every point on its input set. So this is right invertibility. And in order for this to work, this is f of g, sorry. In order for this to work, right, in order for this to work, in order for this to work, G has to be surjective, because otherwise this wouldn't make sense on values on which f isn't defined. So let me draw a diagram. So this is equivalent to surjective. And this is equivalent to injective. So sur is a Latin or French prefix that means onto. Surjective mappings are often by older mathematicians. You'll hear them use the word onto. Surjective and then injective. So the way I think about this, so the kind of second grade picture of a function you might have is you have this set over here A and this set over here B, and A, say it has 5 buttons and B has 5 buttons. This is maybe a good illustration for what we're going to be talking about. So as long as it's allowed to like cross wires and stuff, so here maybe is an even better illustration. This is not a function. Okay. For two reasons. Number one, it's one-to-many, and number two, that you're not allowed to have partially defined functions. Here is an example of a function. So if I have 3 buttons over here and only 2 over here, this is a function. By the way, there's a, you could, if you flipped the arrows, this would be a function that would not be injective because it's many to one. This is injective because it's one to one, but it's not surjective because there's a point over here that we miss. Okay, and bijective means it just, bijective would mean you have 2 buttons over here, 2 buttons over here, and you're just mapping between them. Okay, that's what those terminologies mean. This is bijective. Bijective means, in particular, if you talk about a bijective function from a set to itself, it just rearranges things. Those are called permutations, and that's the subject of this chapter, so let's get back to it. A permutation of a set S is a bijective map from a set... Okay, I'm going to do this. Is a bijective map from a set S to itself. So here, maybe if you drew this as 1, 2, 3, maybe I will draw that. I can't see the pointer in this program. Okay, I'm just going to go 1, 2, 3, 4, 5. It's amazing how important the little adjustments the drawing program makes to my handwriting are, because it is so much worse over here. So this goes 1 to 3. Let me make that thinner. It goes 1 to 3. 2 goes to 5. Is there a way for me to force a straight line? I'm sure there is, but it's not worth it. 2 goes to 5. 3 goes to 4. 4 goes to 1. And 5 must go to 2. Yeah. So notice this is just rearranging things, and this is completely invertible. It's injective, meaning it's 1 to 1. It's a 1 to 1 mapping as opposed to a many to 1 or 1 to many mapping. It's a function because every point in the domain is hit, and it's surjective because every point in the codomain or the target space is hit. So anyway, the table, which I just drew out, exhibits a permutation P of the set 1, 2, 3, 4, 5 of the 5 indices P of 1 equals 3, etc. It is bijective because every index appears exactly once in the bottom row. Alright. The set of all permutations of the indices 1 to 2 up to n is called the symmetric group and is denoted by Sn. It will be discussed in Chapter 2. The benefit of this definition of a permutation is that it permits composition of permutations to be defined as composition of functions. Boy, how long is this section? Oh boy. Alright, let's just power through it. I might, if there's some hairy proofs, we're gonna do what we did last time and split it up into multiple videos. Symmetric group. Alright. The benefit of this definition of a permutation is that it permits composition of permutations. Where are we? We're over here. The benefit of this definition of a permutation is that it permits composition of permutations to be defined as composition of functions. Right? If Q is another permutation, then doing first P then Q means composing of the functions Q of P, right? This composition is called the product permutation and will be denoted by QP. Note, people sometimes like to think of a permutation of the indices 1 up to n as a list of the same indices in a different order as in the bottom row of 1.5.2. This is not good for us. Right, in math, one wants to keep track of what happens when we perform 2 or more permutations in succession. For instance, we may want to obtain a permutation by repeatedly switching pairs of indices. Then unless things are written carefully, keeping track of what has been done becomes a nightmare. The tabular form shown above becomes cumbersome. It is more common to use cycle notation. Why do you have QED here, dude? The tabular form shown above is cumbersome. It is more common to use cycle notation. To write cycle notation is wonderful. Okay. Oh boy, this is some geogritude. You're gonna love this. So to write cycle notation, you just begin with an arbitrary index and follow it along. The string of 3 indices forms a cycle from the permutation, which is denoted by 3, 4, 1. And so you compose these right to left, but you read each one left to right. It's like reading numbers in Arabic. It's good water. 3, 4, 1. This notation is interpreted as follows. The index 3 is sent to 4, the index 4 is sent to 1, and the parentheses at the end indicate that the index 1 is sent back to 3 at the front by permutation, right? Because there are 3 indices, this is a 3 cycle. Also, P of 2 equals 5 and P of 5 equals 2, so with the analogous notation, the 2 indices 2, 5 form a 2 cycle. 2 cycles are called transpositions, right? The complete cycle notation for P is obtained by writing these cycles one after the other, right? You can read off the permutation If you have disjoint cycles, then it doesn't matter how you transpose them. Or how you multiply them. It's commutative as long as the cycles are disjoint. That's important. If the cycles aren't disjoint, then you got some fun stuff going on. One slight here's the point he's making. One slight complication is that the cycle notation isn't unique for two reasons. First, we might have started with an index different from 3, thus 3, 4, 1, 1, 3, 4, and 4, 1, 3 are notations for the same 3 cycle. Second, the order in which the cycles are written doesn't matter, as long as they're disjoint. Cycles made up of disjoint indices can be written as in any order. We might as well write 5, 2, 1, 3, 4. The indices, which are 1, 2, 3, 4, 5 here, might be grouped into cycles arbitrarily, and the result will be a cycle notation for some permutation. For example, 3, 4, 2, 1, 5 represents the permutation that switches two pairs of indices while fixing 2. However, 1 cycles, the indices that are left fixed are often omitted from cycle notation. We might write this permutation as 3, 4, 1, 5. The 4 cycle 1, 4, 5, 2 is interpreted as meaning the missing index 3 is left fixed. Then in a cycle notation for a permutation, every index appears at most once. Of course, this convention assumes that the set of indices is known from context. That's true. The one exception for this rule is the identity permutation. We'd rather not use the empty symbol to denote this permutation, so we denote it by 1, right? To compute the product permutation QP with P and Q as above, we follow the indices through the two permutations, but we must remember, right, that QP means Q of P, which means first do P, then do Q. So since P sends 3 to 4 and Q sends 4 to 5, QP sends 3 to 5. Unfortunately, we read cycles from left to right, but we have to run through permutations from right to left. There's no reason you have to do that. It's just you choosing to be retarded in a zigzag fashion. This takes some getting used to, but in the end is not difficult. All right. The result in our case is a 3 cycle. Right. QP equals, he found stack rel. First do this, then do this. So let's follow the 2. Can't see my point. 2 goes to 5, which goes back to 2. Okay, so 2 is left fixed. 1 goes to 3, which is left fixed, so 1 goes to 3, that's right. What happens to 3? 3 goes to 4, which then goes to 5, so that's fine. 4 goes to 1, which goes back to 4, so 4 is fixed. And then 5 goes to 2, which goes to 1, so 5 goes to 1, so yeah, this is the correct answer. Right, and he's showing by example, because they're not disjoint, composition, right, if the two cycles are disjoint, then they're commutative, but these two are not disjoint, they have indices in common, so it's not commutative. So when we commute it one way, if we multiply it one way we get 1, 3, 5, the other way we get 2, 3, 4. Composition of permutations is not a commutative operation. Oh, permutation matrices, wonderful. There's a permutation matrix P associated to any permutation P. Left multiplication by this permutation matrix permutes the entries of a vector X using the permutation P. For example, if there are 3 indices, the matrix P associated to the cyclic permutation P equals 1, 2, 3, and its operation on a column vector are as follows. Px equals 001, 100, 010 times x1, x2, x3, which gives us, right, x3, x1, x2. Yeah, that's right. Multiplication by P shifts the first entry of the vector x to the second position, and so on. It is essential to write the matrix of an arbitrary permutation down carefully, and to check that the matrix associated to a product PQ of permutations is the product matrix PQ. This is hinting at something called representation theory, which is important. Everything in math is important, but representation theory is very important. The matrix, right? A transposition will be well, it'll be a transposition matrix. It'll be an elementary matrix. The matrix associated to a transposition 2, 5 is an elementary matrix of the second type, the one that interchanges the two corresponding rows. This is easy to see, but for a general permutation, determining the matrix can be confusing. To write a permutation matrix explicitly, it is best to use the n by n matrix units, oh boy, Eij, which is the matrices with the single 1 in the ij position that were defined before. Oh god. The matrix associated... Why is this better? Oh my god. Okay. I told you Artin glows in the dark. This is some glow-in-the-dark stuff. The matrix associated to a permutation P of Sn is P is equal to the sum over I of E sub Pi comma I. Oh, now you know what commas are. Not when you were not in the last chapter. You didn't know what commas were. Lovely. Oh wait, no, he doesn't have a comma up here. There's no comma here, but now he knows what commas are. All right. In order to make the subscript as compact as possible, we've written Pi for P of I. All right. Just as glow-in-the-dark shit. We switch to green because we're glowing in the dark. This matrix acts on the vector x as follows. Alright, I gotta decipher this equation and then tell you what it means. Px equals... okay, so it's the product of two sums. So this is the vector x. So this is where is it? This is a column vector. And this is a permutation matrix. Okay. And then this is the sum over ij of okay. Right. Which is right, because if I is not equal to j, then those terms will cancel out. Of EPI, I, EI, XI. What the hell is E sub PI? What is this? Oh, okay. So this is saying this is a column vector. So it's okay. That makes sense. I'm sorry, I can't explain the notation. If you So part of the thing is he's mixing types here. So this is a n by n matrix. This is n by 1 matrix, and this is a number. Okay? So he's taking a weighted sum of n by 1 matrices and summing over all the possible indices, and that's how he's getting a column vector. So he's writing, 1, 2, 3. He's writing this as, if this is a column vector, as 1 times 1, 0, 0, plus 2 times 0, 1, 0. This is E1, E2, plus 3 times 0, 0, 1. And this would be E3. That's what this notation means. Okay? This So this EPII is a matrix that has a 0 everywhere except for in the P of I, comma I row column pair. He better have some examples. Okay. I mean, I understand, but this notation is just, my God. Okay. Sum over ij. Okay, we can just, right, because right, each row will have exactly 1, 1 in it in a permutation matrix, and each column will have exactly 1, 1 in it. So you only need to loop over the rows. Okay, so that's why you can do a single sum here. Okay, it's kind of like Sudoku almost. Sudoku is a kind of a good example. Good way to familiarize yourself with this kind of logic that we're going to be doing would be to watch some Sudoku, or do some Sudoku. I can't do Sudoku, so I just watch other people. I mean, look at this. So this is an n by n matrix times an n by 1 matrix times a scalar times a number. Okay, and this will produce an n by 1 matrix, and it's a sum, it's a double sum over a bunch of n by 1 matrices, most of which are 0 when I is not equal to j, because then you have something like, you know, you have something like, you know, this, which if you do out that matrix multiplication, that's just going to be all zeros. So if I is not equal to j, so this would be E1, 1, and this would be E3, since 1 is not equal to 3. Right, it's only gonna not be 0 if we were to write this in my tabular form, 1, 0, 0. Now I'm going to run out of page. 0, 0, 1, then you can kind of do the zipping in your head, and it's a little bit easier to visualize. We're only going to see on EJ, so this is E3, we're only going to see non-zero answers if this column over here is not 0, which happens if this is, you know, if we're doing where are we? Okay, if we're doing E sub kj and E sub j, then you'll get something that's not 0. Or let me instead do it E sub ij, which means that you have a 1 in the jth column, and then ej, which means you have a 1 in the jth column. This will equal ek. This will equal E sub L. Oh. This will either equal, I'm going to put a case statement in here. If j is equal to k, then this is E sub j, or which is equal to E sub k. If j is different from k, this is going to be the 0 vector. That's the whole logic of this equality sign right here, is this. Okay? That's why you can delete the j's and only sum over, switch this index right here from a j to an I, and this index from a j to an I. Okay, well then EPII EI, no, this will equal EI. This over here, my mistake, this will equal E sub I. That's the point. Then we get an E sub pi over here. Alright, that makes sense. Alright, sorry about that. I made a mistake. Alright, to try to rewind the video and dissect what I just said. I think I ended up getting something correct. Okay, that makes sense. I mean, the notation is garbage, but it makes it, if you unwind it, you know, it makes sense. The computation is made using formula. I'm not going to go look that up. The terms, right, that's what I just said. The terms E, Pi, I, E, J in the double sum are 0 when I is not equal to j. To express the right side of 1.5.8 as a column vector, we have to reindex so the standard basis vectors on the right are in the correct order, E1 to En, rather than in the permuted order EP1 to Pn. We set Pi equals to k and I equals to P inverse k. Then, right, okay, then this is just an identity. Sum over I of E sub Pi xi is equal to sum over k times E sub k x P inverse k. Remember, since it's a bijective mapping, you can do that inverse thing. E sub k x sub P inverse k. This is a confusing point. Permuting the entries xi of a vector by P permutes the indices by P inverse. That's interesting. Yeah, that might have been what I was getting hung up on earlier. For example, the 3 by 3 matrix P of 1.5.6 is E21 plus E32 plus E13, and Px, you know, finally, oh no, we have a proposition, which means one of his horrible proofs. Alright, is E21 plus E32 plus E13, E1x1 plus E2x2 plus E3x3 equals E1x3 plus E2x1 plus E3x2. Okay. I don't feel like doing the distribution on that because I'm lazy and I'm tired and I don't know how long has this video been going? 47 minutes, Jesus Christ, and we're not even like a little bit done. Oh wait, can never. Oh, we're almost done actually. Okay, is it worth me expanding this out? Yeah, you know what? I'm going to expand this out. Okay, it's probably worth it. Let me zoom out. Why don't I do it like this and then that? That way. Okay. To just give you an example of what was going on up there. Okay. So we have P is equal to E21 plus, I'm not going to bother with my good ones, sorry. No, I need to do, this is precisely when I should be bothering with my good ones. Because then I will get in the habit, because now it's expensive to stop. Okay, and if I write this out as a matrix, this would be E21, so go down 2, 1, 3, 2. Scroll back in the video and check if that's what we got before. That looks right. Okay. Plus E1x1 plus E2x2 times E2x3. So that's P. And then X would be X1, X2, X3. Okay. And then if we do out, and then let's just do the matrix multiplication by hand. 0, 1, 1, 0, 0, 0, 1, 0 in my vastly superior tabular format. I'm the smartest mathematician who's ever lived. X2, X3, this will give us x3, x1, and x2, which is e1x3 plus e2x1 plus e3x2. So we get the same answer if we do normal matrix multiplication. And if we, what I wanted to go over is the logic of how these indices, how this index stuff works. So px is equal to e21 1 plus, that looks too much like 2, e3 2 plus e1 3 times e1 x1 plus e2 x2 plus e3 x3. This is equal to, let's, well, Jesus Christ, e2 1 e1 x1 plus e2 x2 plus e3 x3 plus e3 2 e1 x1 plus e2 x2 plus e3 x3 plus e1 3 times e1 x1 plus e2 x2 plus e3 x3. Okay. Which is equal to e21 e1 x1 plus e21 e2 x2 plus e21 e3 x3 plus, Jesus Christ, e3 2. Okay. Plus e3 2 e3 x3. I'm getting carpal tunnel. Plus e1 3 e1 x1 plus e1 3 e2 x2 plus e and if I've made a mistake, there is zero chance I've caught it. And the point of that so let me give you what each step was. Okay. So this first line right here is this step right here. That's what this is. This second one is just doing the distribution, I guess. So now we're here is this step. Okay, and now the step I'm about to do is getting to this step, which is to say, well, the only non-zero terms, let me highlight them, are going to be where the lower index matches, where the right index here matches the index here. So it's going to be this one, and this one. And all of the other terms are going to, we can cross them out because they're going to be 0 by just our matrix multiplication logic. Okay? And this is how you get the sum over I thing, which would be e2 1 e1 x1 plus e3 2 e2 x2 plus e1 3 e3 x3, of course, which is equal to e2 x1 plus E3x2 plus E1x3. Okay. So notice now we've permuted the vectors E1, E2, E3. Oh boy, I'm getting confused. Right, which is E1x3 plus E2x1 plus E3x2. So I got that right. Okay. Okay, that's fine. Proposition 1.5.10. A permutation matrix P always has a single 1 in each row and in each column, the rest of its entries being 0. Conversely, any such matrix is a permutation matrix. The determinant of a permutation matrix is plus or minus 1. All right. Let P and Q be permutation. Oh, great. More of this. I'm just looking ahead at the proof and going, I don't want to read that, but I guess I will. Let P and Q be two permutations with associated permutation matrices P and Q. The matrix associated with the permutation PQ is the product big P, big Q. Of course, you omit verification of A and B. Lovely. Computation below proves C. I would say that any transposition, so the way I would prove that would be to do the, there's a theorem which says that any permutation can be decomposed into a product of transpositions, and then you can write each of the transpositions as one of those elementary matrices, and then, you know, that will give you that theorem. Just making sure I'm recording with the right microphone. Oh boy. Alright. Zoom in. Zoom out. That's too far in. Okay. Okay. PQ equals the sum over I of PI sub comma I. So these are two n by n matrices. It's equal to the sum over ij of EPII EQJJ. Oh, God. I have no idea why that is true. There's a formula apparently above that would give you this computation. EPII EQJJ. EPQJ QJ EQJ QJ. I have no idea where. Okay, I understand this step. I have no idea where this comes. This step, I have no idea where this comes from. This step kind of makes sense a little bit. No idea about this step, and I'm too exhausted to go look. Maybe I'm gonna have to. I might have to do another video going back and let me put some stars next to this for do better. Specifically, figure out this. This and this step. Okay. That's a note to myself. Note to self. Do better proof. Or / verify. To self. Okay. The terms EPI EQJJ in the double sum are 0 unless I is equal to QJ. Okay, that kind of makes sense. So it's saying that you can what this is saying is that if you have permutations, you can port the permutations into matrices, and the matrix multiplication works the same way as, or is compatible in the sense that maybe a way to think about it is as a functor, is that if you, okay, let me get two permutations. And what this is saying is that convert into matrix. Let me draw a diagram. This arrow is multiply permutations. And let's call the matrices pi 1, pi 2. Multiply matrices. So p pi. This arrow is still convert. And each step here is reversible, provided you know the initial ingredients. What it's saying is that it does. What this theorem is saying is that it doesn't matter which order you go. You can go this way. That's fine, or you can go this way, and you'll end up at the same result. That's what this theorem is saying. The sign of the permutation, right, is the determinant of the permutation matrix. That's another interesting facet of this. So the sign is the determinant, which I always thought as the number of transpositions. Right. Okay. Permutation p is even if its sign is +1, and odd if its sign is -1. Okay. The permutation 1, 2, 3 has sign +1. It is even while any transposition has negative sign. Right. Right. Every permutation can be written as a product of transpositions. This is how I would prove the chapters 7 and 10, and I'm guessing one of those chapters is about representation theory. Okay, every permutation can be written as a product of transpositions in many ways. If a permutation p is equal to the product tau 1 down to tau k, where tau I are transpositions, right, the number k, right, and you think about this in terms of the determinant, where the transposition matrices in the elementary matrices have negative determinant, and so you have to have an even number of negative numbers in order for the total sign to be 1. The number k will always be even if p is an even permutation, and will always be odd if p is an odd permutation. Right. This completes our discussion of permutations and permutation matrices. We will come back to them in chapters 7 and 10. That's all I have for Artin, but I want to go look and see what chapters 7 and 10 are about, and I bet one of them is about representation theory. Well, let's scroll all the way back up to the table of contents. Chapter 7, more group theory, okay. And 10, group representations. What did I tell you? It's representation theory. Alright, that's all I have. Thank you for watching if you watched all the way to the end. Hope you learned something. Yeah, I'll see you in the next video. I don't know what I'll talk about in the next video. Did I save this? I meant to save this. Alright, thank you for watching. Bye.